Okay, hi AP Chemistry class, Hoover High. This is your problem set for Thursday evening, September the 12th. It's a little lengthy, so I'm going to kind of rush through it. Stop as you need to, rewind, go back, or rewind, but go back, click back, and you need to watch something a second time. So, really important number in chemistry is Avogadro's number. Avogadro's number is 6.022 times 10 to the 23rd. It's known as Avogadro's number. We're going to talk about why that's an important number today. Now, when you're talking about in terms of doing chemical calculations, you don't say you use Avogadro's number. You refer to it as a mole. And so what is a mole? It's Avogadro's number. It's the same thing. Okay, again, I'm just giving you some basic definitions to start you off. So atomic mass is the mass or weight it's the mass of an atom. Sometimes it refers to the mass of a molecule as well, or that can be called molecular mass. It's not really picky about which term you use. You can refer to a molecule as having atomic mass. Okay, mass number, we said, is when you round the atomic mass to the nearest whole number. That will tell you how many protons and neutrons you have in that atom. So it's atomic mass rounded to a whole number. Okay, molar mass. Now, what is the molar mass? If the atomic mass is the mass of one atom, then if you take this number of that same atom, that will give you the molar mass. So the molar mass is the mass of a mole of a particular atom. And here's one of the key differences. The number of the molar mass and the atomic mass of that particular element are going to be the same, but the atomic mass is measured in atomic mass units. Remember, that's the mass of a single proton or a single neutron, whereas the mass of a mole of atoms, I should say a mole of atoms, is measured in grams, which is a much more useful unit to us because we have scales in the back of our classroom that can measure things in grams. So that kind of brings up the distinction between microscopic, that would be molecules, atoms, things that are so small we can't really see them, but yet truly that's where the action is taking place in chemistry. And macroscopic, that's the things we can actually see in our everyday world. It's a large enough number of atoms and molecules that we can actually see them and weigh them on a scale. That's called the macroscopic. So chemistry is kind of a mixture. Studying chemistry is a mixture of studying the macroscopic, which we can observe, and inferring from that what the microscopic is, what's going on at the atomic and molecular level. Okay, finally, let me introduce you to one word, although we're not really going to deal with this today, but stoichiometry is the math of chemistry, and specifically the math of chemical reactions. And we're going to get into some of those tomorrow. All right. So what we're going to do in this first part of the exercise, and we'll move quickly through this because there's a lot of these, is we are going to calculate the atomic mass of some of these compounds up here. It's everything from carbon dioxide to cinnamon, vitamin C, aspirin, things like that. You notice how many of them, particularly those that go into food products or things that you can take into your body, are C's and H's and O's. There's a lot of that there, okay? All right, so here's an example. And by the way, in this example, I rounded. I did that with my regular chemistry students. I don't do that with AP students, though. So hydrogen has two atoms of water. We're talking about H2O here. So all we're going to do is figure out what's the atomic mass of water. Okay, so hydrogen, there's two atoms, and each atom has a mass of 1 or 1.001, actually, to be more exact. Okay, so I rounded this to 1, but you see from your periodic table, you should have a periodic table present or pull one up on the internet that gives you atomic masses. And you see I'd rounded it to 1 for hydrogen, but it's really 1.01. And you multiply that by 2. So this would really be 2.02, but we'll just call it 2 for this example. Oxygen actually is 16, and there's only one oxygen atom. So the mass of the oxygen in a water molecule is 16. So if you add those two together, you get 18, or if I'd been more precise, it's 18.02. So if you're wondering how I knew how many water molecules were in that bottle today in class, it's because I knew that I had 18.02 grams of water in there. We're going to talk about that, and that's how you make these conversions. But the one water molecule is 18 or 18.02 atomic mass units for a single water molecule. Okay, let's keep rolling here. So we're going to do this I'm going to do this for a couple of these. I don't want to belabor this. I think this is one solution video where I'm not going to do every single one of them. I think once you've seen a couple of them, you'll get the idea, and I'll let you do the rest, okay? So let's do acetic acid here. So acetic acid is C2H4O2. So I'm going to put a C, an H, and an O here. Okay, and then I'm going to put the entire chemical compound here. And what these subscripts mean is that's how many atoms of each of these elements you have in this molecule. Notice that these are nonmetals. They're covalently bonded, and they form independent structures called molecules. Okay, so the number of atoms is, for carbon is 2, for hydrogen is 4, and for oxygen is 2. Okay. Now, when you put together the 2 atoms of carbon, the 4 of hydrogen, and the 2 of oxygen, you don't end up with 2 plus 4 plus 2 or 8 molecules of C2H4O2. You end up with 1 molecule. So these are the parts that make up this 1 molecule of C2H4O2 of acetic acid, which, by the way, is vinegar. All right. Now, the atomic mass, and I'm not going to be rounding here. Okay, so I'm going to be going from the periodic table that you were given in class. So the atomic mass of hydrogen, to 2 places after the decimal, 3 significant figures there, is 1.0, for carbon, I apologize. For carbon is 12.01, straight from the periodic table, times 2. You multiply that, you get 24.02. So that's the mass of the carbons that are in acetic acid. Hydrogen, we do the same thing. From the periodic table, we're not using mass number, we're not rounding it. We're actually taking the actual atomic mass times 4, and that's going to give us 4.04. And finally, oxygen is going to be 16.00 times 2, and that equals 32.00. Okay, and actually I should have written those over there, so I'll do that. So 24.02, 4.04, and 32.00. Okay, and so we add those up, and you want to check my calculations. I don't always add things correctly. I try. We all want to get more accurate, and that's what we get. And now we're talking about a single molecule of acetic acid, so the measurement is in AMU, and actually we should write that up here on the top of the table, in AMU. Everything down here is in AMU. Okay, so that's the mass of a single acetic acid. Okay, let's do carbon dioxide. That's an easy one. CO, there's 1 carbon, there's 2 oxygens. The atomic mass for carbon is 12.01. You multiply that by 1, you get 12.01. For oxygen, it's 16.00 times 2 is 32.00. And you add those together, you get 44.01 AMU for carbon dioxide. That's the weight of a molecule of carbon dioxide, 1 molecule. Okay, I'm going to do one more of these, and then we're going to move on to the second part of this assignment. Let me go ahead and do that. Let me get this adjusted. Okay, so let's do vitamin C. Again, a compound with carbon, hydrogen, and oxygen in it. So you see that most of your body is made up of these nonmetals. And that's why you're ingesting them. That's why you're taking them in. Okay, so for carbon, we have 6. Hydrogen, we have 8. Oxygen, we have 6. So it's going to be, for carbon, is 12.01 times 6. For hydrogen, it's going to be 1.01 times 8. And for oxygen, it's going to be 16.00 times 6. Okay, so 12.01 times 6 is going to be 72.06. And for hydrogen, it's going to be 8.08. And for oxygen, it's going to be 96.00. And you add these up, and what do we get? 168, 176, 177.14. 0.14 AMU. Okay, and I've checked that. I just realized that's 176.14 AMU. Okay, so there we go. So that's the whole idea of how to calculate the atomic and then molecular masses of compounds. Okay, so we just figured out how to figure out masses of very small little things called molecules and atoms measured in AMUs, but somehow we have to make the transition to how we can make measurements in the macroscopic world, the world that we can see and weigh and measure, and it's actually things that are big enough for us to do that. So what we do is we take this magic number called a mole, and we just decide that's going to be a standard number of atoms and molecules we're going to work with. So instead of saying we're working with one carbon atom or one water molecule, we're going to work with a mole, 6.022 times 10 to the 23rd carbon atoms, or 6.022 times 10 to the 23rd water molecules. And that's going to give us a big enough quantity of them that we can actually see them or actually weigh them, and we can work with them. The question that comes up is, why did they pick this funny number, 6.022 times 10 to the 23rd? Why didn't they pick 1 times 10 to the 20th? That would have been 1 with 20 zeros after. That's a big number. They could have picked any big number they wanted. Why did they pick this big number? So you're going to see that here in this table right here. Let's go back and talk about carbon dioxide. So let's do what we just did, review what we just did. We have a carbon and an oxygen. We have 1 atom of carbon and 2 atoms of oxygen in CO2. So you put those 1 carbon and 2 oxygens together gives you 1 CO2. Again, you don't add these numbers. When you build a motorcycle, it takes 2 wheels and 1 motor to build 1 motorcycle. So be careful, you're not adding the number of atoms or molecules there. So let's figure out the mass in AMU. And again, I shortcutted this. I should have, I didn't put the decimals here, but I have 1 carbon times 12, or 12.01 to be exact, is 12. 2 times 16 is 32. When you add them up, you get 44, or 44.01 to be exact, AMU for the carbon dioxide. Okay, that's great, but that's right back where we were before. It's too small for us to work with. So they decided, let's call a big number a mole. And so instead of dealing with 1 atom of carbon, we're going to deal with 1 mole of carbon, and that's a big enough number for us to use. Again, they could have called any number a mole, any big number. So why did they choose this one? Well, this is where the next column comes in. If I have 1 carbon atom, it has a mass, we already said, of 12.01 atomic mass units. If I multiply that by this many carbon atoms, I get this number right here. Look at that, 12 and 12. Okay, so the magic of Avogadro's number, 6.022 times 10 to the 23rd, is that if I have 1 carbon atom with 12 AMU, I get exactly the same, 1 mole of that will give me exactly the same numeric value, but in grams. And that's a useful measure that we can actually put on a scale. So 6.022 times 10 to the 23rd is the only number there is that'll convert 12 atomic mass units for carbon into 12 grams for a mole. And that's why this number is so special. And that's why we can now work with 12 grams, whereas 12 AMU was too small for us to work with. Same thing with oxygen. It's 32 AMU for 2 oxygen atoms put together. So if I take a mole of that, I will end up with 32 grams of oxygen. So it's the same numeric value, 32 and 32. And you notice the same thing happens for the total for carbon dioxide, it's 44 and 44. Okay, and then over here, what I do is I just want you to count the number of atoms or molecules just to realize, what this is saying. We have 1 mole of carbon. Again, a mole is a number just like a dozen, okay? Dozen is 12 of anything. It could be 12 eggs, 12 pizzas, 12 people. It just means the number 12 when you say dozen. When you say mole, it means 6.022 times 10 to the 23rd. So if I have 1 mole of carbon, 6 times 10 to the 23rd, 6.022 times 10 to the 23rd. If I have 2 moles of oxygen, as I do here, then it's 2 times 6.022 times 10 to the 23rd. You don't really have to do the math right there. It's just to show you that, but just so you understand the concept. And we end up with 1 mole of carbon dioxide, which is 6.022 times 10 to the 23rd molecules of carbon dioxide. Okay, let me do a couple of corrections here. For K2O, it shouldn't say how many water molecules, it's just how many molecules is in a mole. And on the next page, still dealing with KO2, these are some questions I'm going to ask you after you fill out the table. It says how many carbon atoms. That was an error. I changed the compound. And so you can scratch carbon and change it to potassium. So K, how many potassium atoms? How many grams of potassium? And that's the letter K. Okay, so let's work through the potassium oxide. Okay, so element is K. Oxygen is here, and we end up with K2O. All right, so the number of atoms included. Well, for K, there's just there's 2 potassiums, and for oxygen, there's just 1 oxygen. And those 2 potassiums plus 1 oxygen give you 1 molecule of K2O. It's actually an ionic compound because it's metal, non-metal. I'm calling it a molecule. It's really a formula unit, but let's not worry about that distinction right now. Okay, so there you go. So the atomic mass for potassium is going to be 39.10. And multiply that by 2. And we get 78.20. Okay, same for oxygen. Oxygen is 16 times 1 oxygen atom, and that gives you 16 in that compound. You add those 2 together, so you don't add the number of atoms of each, but you do add the atomic mass, and you end up with 78, 88, 94, 94.2. I'm going to check my math on a calculator here. 94.20. Okay, there's the decimal point there. Okay, 94.20. Okay, so now we're dealing with atoms and molecules here. That's too little. We can't work with those. So we need to get a bigger bunch of them. We need to get a big basket. So we decided we were going to take this magic number 6.022 times 10 to the 23rd. That's a mole. So we have 2 potassium atoms here, and we multiply that by 6.022 times 10 to the 23rd, we end up with 2 moles of potassium. If we have 1 atom of oxygen and we multiply that by 6.022 times 10 to the 23rd, we end up with 1 mole of oxygen. And the same with the compound K2O, we end up with 1 mole of that compound. So moles to moles just match up, the numbers match up. But what the magic of this number is that if we take this atomic mass or molecular mass down here for K2O, and want to know what the molar mass is, the mass of that many, it's exactly the same number, 94.20, but it's in grams, a unit that we can measure on a scale. So I'm going to do the same 78.20, that's atomic mass units. And again, it is not rounded. Okay, so that's going to give me 78.2 grams. And same thing for the 16 here. it's 16 grams of oxygen. So if I want to start making a compound of K2O, I know, how many grams, because I can measure 78 grams on a scale of potassium. I know how many grams of oxygen. I can measure that in a scale, so we're all good. Now the last thing I ask you to do is just tell me how many actual particles or atoms or molecules that is. So if it's 2 moles, then it's 2 times 6.022 times 10 to the 23rd. Okay, for oxygen, it's 1 times 6.022 times 10 to the 23rd. And finally, for the entire compound K2O, it's 1 times, I have 1 mole, 1 times 6.022 times 10 to the 23rd. Okay, there we go. So we filled out the table just like the carbon dioxide above. Now I'm going to ask you to answer some questions. And this is just like cooking. Okay, so let's look at a couple of examples here. What it's saying is, circle this number right here, 1 mole on the line of K2O. What it's saying is, if I want to make 1 mole of K2O, I need 1 mole of oxygen, 2 moles of potassium. I need 78.2 grams of potassium. I need 16 grams of oxygen, and 1 mole of that would be 94.2. So what if I wanted to make 2 moles of K2O, how many moles of potassium would I need? Just throwing out an example problem. Well, it's just like if I need 1 cup of sugar to make 1 cake, and I want to make 2 cakes, then I need twice as much sugar. So if I needed 2 moles of potassium to make 1 mole of K2O, and I want to make 2 moles of K2O, then I need twice as much potassium. That would be 4 moles. You just double the ingredients that you're putting in. It's just like cooking. Okay? All right, so let's answer these questions. How many molecules in 1 mole of K2O? So here it is, 1 mole, and over here is the number of molecules. 1 mole of anything has 6.022. That's Avogadro's number, that's a mole, times 10 to the 23rd. Normally I want you to write these out as complete sentences, but this is a fairly long assignment, so I'll let you get away with just some short answers. Okay, how many grams is 1 mole of K2O? So here's 1 mole. And how many grams is it? It's right there. It's 94.2 grams for 1 mole. And here's the way you should write this actually. Write it grams and then in parentheses, grams of K2O. So unit of measure, which is grams, and then the substance we're talking about. Otherwise, we could get confused. Maybe we're talking about grams of oxygen. Maybe we're talking about grams of potassium. So be sure you have the unit of measure, in this case grams, and what you're referring to of K2O. And get in the habit of doing that, okay? Otherwise, you can get very confused later on in chemistry problems. Okay, let's keep going. All right, I'm going to try to kind of squeeze the table onto the screen. I'm on the next page now. Okay, so get this here. Okay, so there we are. There's our table. I'm going to lower it there. The next question is, number 3, is how many moles of oxygen in 1 mole of K2O? So in 1 mole of K2O, we look right up above, there's 1 mole of oxygen, okay? So you can just write 1 mole of oxygen. Next question, how many grams of oxygen in 1 mole of K2O? So 1 mole, we're going to need 16 grams. It's 1 mole of oxygen, which is 16 grams. So there's 16 grams of oxygen in 1 mole of K2O. Again, everything here is scaled to 1 mole. If we need more than 1 mole, we got to scale everything up accordingly. How many potassium K atoms are in 1 mole of K2O? So there's 2 moles of potassium atoms for every mole of K2O. You needed 2 potassiums to make 1 mole of K2O. So the answer is 2, and you don't have to do the math on this, 2.022 times 10 to the 23rd. You just show it so you understand the concept. It's 2 moles, 2 times a mole. Okay, and finally, how many grams of potassium K in 1 mole of K2O. So there's 1 mole, and to make 1 mole, we needed this many moles of potassium, which would weigh this many grams, 78.2 grams. So the answer is there's 78.2 grams of potassium in 1 mole of K2O. Okay, that takes care of that one. Let's do another. Let's do H2O. Let's do water. So I'm coming down here. Let's fill out the table. Let's see how quickly we can do this, but let's do it accurately. Okay, so I have H and I have O, and I have down at the bottom H2O. Okay, atoms. I have 2 hydrogens, I have 1 oxygen, and that produces 1 molecule of water. Okay, again, motorcycle is 2 wheels plus 1 motor gives you 1 motorcycle. Okay, so 2 hydrogens plus 1 oxygen gives you 1 H2O. Okay, the atomic mass, and we're going to go to not rounded, we're going to go to actual decimal numbers, is 1.01 times 2, and that equals 2.02. So there's 2.02 AMU of hydrogen in 1 water molecule. Oxygen is 16.00 times 1, and that's going to mean there's 16.00 AMU in 1 water molecule. You add those together and you get 18.02 AMU in a water molecule. Okay. All right. Now, number of moles. Well, all we're doing is we're taking our 2 atoms of hydrogen, multiplying it by 6.022 times 10 to the 23rd, and that'll give us 2 moles of hydrogen. So we have 2 moles. Numbers always match up. We're taking 1 atom of oxygen, we're multiplying it by 6.022 times 10 to the 23rd. That gives us 1 mole of oxygen. And the same with water. 1 mole of water is going to be one molecule of water times a mole. It's going to give us 1 mole. All right, so there we go. And now we go over to the molar mass, and this is the magic part of Avogadro's number, is that if we have 2.02 AMU of hydrogen in 2 hydrogen atoms, then we're going to have 2.02 grams of hydrogen in 2 moles of hydrogen atoms. Okay, if we have 16 AMU in 1 oxygen atom, then we're going to have 16 grams of oxygen in a mole of oxygen. And finally, if we have 18.02 AMU for a water molecule, then a mole of water is going to be 18.02 grams. So if you wanted to know how I knew that I had a mole of water molecules in the bottle today in class, it's because I weighed it out. It was 18.02 grams. And I know if I have 18.02 grams, that's 1 mole of water molecules, which is 6.022 times 10 to the 23rd. Okay, so that's the beauty of this number and how you can figure things out. Okay, let's finish up this column and we'll be done with this video. So how many atoms or molecules of hydrogen? We have 2 moles, so that's 2 times 6.022 times 10 to the 23rd. Hydrogen atoms total. Okay. Of oxygen atoms, we have 1 mole of oxygen, so we have 1 times 6.022 times 10 to the 23rd. And finally, water molecules, we have 1 times 1 mole, or 1 mole, 1 times, 6.022 times 10 to the 23rd. And that's how many water molecules we have. So now, down below, I'm asking you some questions here. So everything that I have over here in the last 3 columns is based on 1 mole of water. So 1 mole of water is going to have 1 mole of oxygen. 1 mole of water is going to have 2 moles of hydrogen. 1 mole of water is going to have 2.02 grams of hydrogen. 1 mole of water is going to have 16 grams of oxygen. And 1 mole of water is going to have a mass of 18.02 grams for that 1 mole of water. So let's answer these questions. So how many water molecules are in 5 moles of water? Well, a mole is that standard number. It's Avogadro's number. So you just multiply 5 times 6.022 times 10 to the 23rd. And you don't have to do the math on it, just so long as you understand the concept. It's 5 times 6.022 times 10 to the 23rd. Now, how many grams is in 2 moles of H2O? Well, 1 mole of H2O is 18.02. So again, it's just you're baking a cake. If you want twice as much, you got to have twice as much. So it's going to be 2 times 18. Show your calculation so when you go back to review this sheet, you know where the number came from. So it's 2 times, if I want 2 moles of H2O, it's 2 times that number of grams, and that's going to be 36.04. And again, put grams, and then put grams of what? It's grams H2O in parentheses. So it's not only the unit of measure grams, but it's what substance are we talking about? Because it could be oxygen, it could be hydrogen. Okay, number 9. How many moles of oxygen in 8 moles of H2O? So for every mole of H2O, I have 1 mole of oxygen. It's a 1-to-1 relationship. So in 8 moles of H2O, I have 8 moles of oxygen. That's just that simple. Okay. How many grams of oxygen in 3 moles of H2O? So if in 1 mole of H2O, if we look up here, I have 16 grams of oxygen for every 1 mole of H2O. So if I want 3 moles of H2O, I need 3 times 16 grams of oxygen. So 3 times 16 grams, and that's going to give us 48 grams of oxygen is needed to make 3 moles of H2O. How many hydrogen atoms in 17 moles of water? Okay, so for every mole of water, H2O, I need 2 moles of hydrogen. I need twice as many moles of hydrogen as I have moles of water. So in 17 moles of water, how many hydrogen? It's going to be 2 times 17, which equals 34 moles. That's my unit of measure. And the element we're talking about is hydrogen. So moles of H. Okay, and finally, how many grams of hydrogen in 3 moles of water? So we look up here, for 1 mole of water, we need 2.02 grams of hydrogen. So if I want 3 moles, I need 3 times 2.02. So it's just scaling everything up, just like you would if you're cooking or baking a cake. Grams, okay? And that gives you 6.06 grams of hydrogen are needed to make 3 moles of water. Okay, so I gave you a lot of these because I want you to really kind of get these to sink in, understand this. You're going to eventually not need to do these tables to do these. You'll be able to do them in your head after you practice enough of these problems. You'll be able to do them very quickly, or at least do them on a calculator really quickly. Okay, so that's it. We'll see you in class, and we'll work on the rest of these tomorrow in class as groups, and we'll share out our answers and see how we're doing. Okay, have a good evening.